Last time we had begun solving the Schrodinger equation in one dimension. The example that we did was the particle in the box, or the infinite potential, square potential. Today we're going to do a somewhat more complicated example, the simple harmonic oscillator. Classically, we describe the harmonic oscillator by Hooke's law, F equals minus kx, which of course is the mass times the acceleration in this case. And the solution, classically, x is a function of time, is a sine omega t plus b cosine omega t, where omega is defined as the square root of k over the mass. The potential, v of x in this case, is 1/2 kx squared. Now, although an ideal harmonic oscillator doesn't exist, almost any potential is parabolic in the neighborhood of a local minimum. That is to say, as long as the oscillations are small, we can approximate that motion as harmonic. Mathematically, we can expand v of x in a Taylor series about its minimum. So let's do that. I've got v of x is v naught of x naught plus v prime of x naught times x minus x naught plus 1/2 v double prime of x naught x minus x naught squared plus higher order terms, which we're not going to worry about. But with this, notice the first term, v naught of x naught, is just a constant. And that's not going to change anything. So we can just subtract that off and not even worry about it. The second term is interesting. This term, v prime of x naught, at x equals 0, the first derivative, that is to say the velocity, if you will, is equal to 0. So the second term also goes away, leaving us with this third term. So we can write v of x as 1/2 v prime of x naught x minus x naught squared. In quantum mechanics, we kind of tend to use omegas rather than k's, and so I'm going to write my potential then for this purpose as 1/2 times m omega squared x squared. So spring constant is out, the classical frequency is in. With that, I can rewrite my Schrodinger equation as minus h bar squared over 2m, second derivative of psi with respect to x. We're doing the time independent equation, 1/2 m omega squared x squared times psi is equal to E psi. And of course, what we want to do in this case is to find the energy eigenvalues and eigenfunctions. I'm going to use two methods. The first one is a rather, it's a clever, diabolically clever, as Griffiths calls it. It's a clever method of solving this, but it's more than that. In fact, as we prepare you for higher level courses in quantum mechanics and field theory and condensed matter field theory and other things, this method is ubiquitous. And if you can learn it at this level and get familiar and comfortable with it at this level, it will serve you extremely well. The second solution that we'll do is the more hardcore differential equation approach. It's a brute force method, to say the least. But it's good to see it at least once. That method is probably one you're not going to use over and over again. You'll just be very happy with the solutions. But the ladder operator approach, this first algebraic approach, is something that you should really pay attention to and try to get familiar with. Okay, so let's start with that. I'm going to rewrite the Schrodinger equation, and I'll rewrite it as 1 over 2m, put in my momentum operator, h bar over I d dx quantity squared plus m omega x squared times psi is equal to E psi. Now I'm going to define two operators, A plus and A minus, and I'm going to define them by 1 over the square root of 2m h bar over I d dx plus or minus I m omega x. Now, operators to be functional have to operate on some function. And so what I'm going to do is operate on a function, some arbitrary function f of x. And I'm going to do it in the following way. I'm going to operate a minus, then a plus on f of x. And when I do that, I'm going to get the following: 1 over 2m h bar over I d dx minus I m omega x. That's the minus version. Then h bar over I d dx plus I m omega x applied to, or operating on f of x. I can rewrite this further as 1 over 2m h bar over I d dx minus I m omega x times h bar over I d of f of x, because I'm applying my derivative here, dx plus I m omega x times f of x. Okay, so what I've done in the second, using the second bracket, is to apply it to f of x. Make sure I take the derivative, of course, with respect to x. Having done that, now I can rewrite this as 1 over 2m times minus h bar over I d dx. Second derivative of minus h bar squared. Second derivative of f with respect to x plus h bar m omega d dx times xf minus h bar omega times mx df dx plus m omega x quantity squared times f. Now when I collect terms, I'll get 1 over 2m times h bar over I d dx quantity squared plus m omega x quantity squared plus h bar omega times m plus h bar omega, h bar omega m times f of x. Put it all together, then we can say, I'll bring this over to this side. We can say that a minus a plus, put it all together, is 1 over 2m h bar over I d dx quantity squared plus m omega times x quantity squared plus h bar omega over 2. We're going to pull the extra h bar omega over 2 to the left-hand side, so we essentially have the Schrodinger equation on the right-hand side. So I'm going to write this as a minus a plus minus h bar omega over 2 is equal to, essentially, what this is just E psi. So it looks like the Schrodinger equation. I can do the exact same thing. I won't do it all out here. I'll leave it to you to do. But you could do the exact same thing with the operation of, rather than a minus a plus, we could do a plus a minus. And if we do that, we're going to get that a plus a minus plus h bar omega over 2 is equal to e psi. So those are, both of these can be called the Schrodinger equation. Left-hand side is essentially the Hamiltonian times psi, and the right-hand side is just e psi. Now, what I will argue is that if the energy E solves the Schrodinger equation, the regular Schrodinger equation, I'm going to argue that A plus operating on psi will give me an energy eigenvalue that's E plus h bar omega. Also, the energy, the operator A minus operating on psi will give me an energy of E minus h bar omega. And we'll just prove the first one. Let's do that. A plus, A minus, plus 1/2 h bar omega. A plus psi is equal to A plus, A minus, A plus 1/2 1/2 h bar omega A plus operating on psi. And I can write that as A plus operating on A minus A plus 1/2 h bar omega times psi. And that's equal to A plus operating on A minus A plus minus 1/2 h bar omega psi plus h bar omega psi. Well, this gives me, this is just in here, this is A plus operating on E psi plus h bar omega psi, which of course is just E plus h bar omega times psi. So it works. And of course you can prove the other as well. And so these are giving me the eigenvalues, the energy eigenvalues for the harmonic oscillator. We call the operators A plus and A minus. In this case, A plus and A minus are called ladder operators. And they take you either up or down the ladder, as it may be. Sometimes we call A plus a raising operator. We call A minus a lowering operator. And these entities will enable you to obtain the energy eigenvalues for the harmonic oscillator. Now, there's more to it than that, and I think we need to kind of spell this out as well. So, what you're probably thinking is, if I apply the raising operator A plus, I apply it to psi once and I go to h bar omega plus 1/2. I apply it again and I go up again. And if I apply it again, I go up again and again and again and again. On the other hand, if I apply the lowering operator, then I'm going to go to h bar omega minus 1/2 and then minus another half and minus and minus and minus and minus and minus. And you might say, well, how do we make sure that this is going to be normalized? So what I have to do is to say, I can't allow energies less than 0. So I'm going to put a lower limit on psi. I'm going to say A minus operating on my lower limit, psi naught, has to give me 0. So that there's a floor on this. I can go no farther below that floor than A minus applied to psi naught. It's what we call the lowest rung on the ladder, if you will. So what that means is, if I write it out, I can write this as 1 over square root 2m h bar over I d psi naught dx minus I m omega x psi naught is equal to 0, which explicitly says d psi naught dx is equal to minus m omega x naught psi naught over h bar. And of course I can solve this differential equation by separating variables, bring the psi naught to the other side, the dx to the other side, and I'll get that log of psi naught is equal to minus m omega x squared over 2h bar plus some constant. Or if I exponentiate, I can say, put another constant in there, psi naught is equal to a naught, this constant, e to the minus m omega x squared divided by 2h bar. We can also determine the energy of that lowest rung by saying, let's do this, a plus a minus plus h bar omega over 2 applied to psi naught is equal to E naught psi naught. So this is essentially the Schrodinger equation. And we know, by the way, that A minus applied to psi naught must equal 0. We've defined it that way. That's the lowest rung on the ladder. Therefore, that being the case, it has to be that h bar omega over 2 is equal to E naught. So the lowest energy rung is equal to h bar omega over 2. This is sort of amazing if you are thinking about classical physics, where there's nothing that says the energy should be the lowest energy should be anything but 0. What the harmonic oscillator in quantum mechanics is telling you is that even the lowest energy for the system has a value, and it's h bar omega over 2. That's our ground state energy, bottom rung. We can generate all the excited states by applying the raising operator over and over and over and over again. And so we may write that out in this way. I'm going to apply, let's say, psi sub n of x would be equal to a sub n. And let's apply our raising operator n times to the function e to the minus m omega x squared over 2h bar, where e sub n in this case is equal to n plus 1/2 h bar omega. That's my energy eigenvalue for the nth energy level. So for example, if I want to go just to the first excited state, psi 1 of x would be equal to a1 times I times omega square root 2m x e to the minus m omega x squared over 2h bar. So that would be, if I put in, if I just did a plus to the first power, that's what I would get for the first excited state. And this is how I would generate all of the eigenfunctions for the harmonic oscillator. As I say, this is an intriguing method. Probably you haven't seen it before, but it's one that you should really get used to. These raising and lowering operators, or as they'll become known later, creation and annihilation operators, when it comes to photons, are just multi-purpose. And so you can learn this technique and feel comfortable with it. It will serve you very well as you move on. Next time, I'd like to do the brute force differential equation solution to the harmonic oscillator. So we'll pick up with that in the next lecture.